Section 240.21.B.1 of the 2002 National Electrical Code addresses feeder taps from busbars larger than 1000 amps. This section stipulates that if a feeder's ampacity is less than 1/3 the busbar's ampacity, the feeder connection must utilize a bolt-on terminal lug, clamp, or a similar approved device. The code mandates a maximum conductor length of 10 feet from the tap to the overcurrent protection device under these circumstances. Now, regarding workspace clearances, the 2002 National Electrical Code does not provide a specific exception for workspace clearances when dealing with feeder taps. However, Section 110.26(E) contains a general exception that might offer some flexibility. This exception acknowledges that deviations from standard workspace clearance requirements may be necessary for maintenance or repairs. Given the described situation where maintaining proper workspace clearances necessitates positioning the fused switch more than 10 conductor feet from the busbar tap point, considering the application of Section 110.26(E's exception is warranted. Here is a recommended approach. Firstly, assess the feasibility of placing the switch in a location that fully complies with the standard workspace clearance requirements. Secondly, if compliance with standard clearances proves impractical, carefully evaluate the anticipated maintenance and repair needs of the switch. If the switch is unlikely to require frequent maintenance interventions, then positioning it beyond the 10 conductor feet limit may be a reasonable solution. Thirdly, meticulously document the deviation from the standard conductor length requirement in the electrical drawings and throughout the project documentation. Fourthly, it is essential to engage with and obtain approval from the local electrical inspector for the proposed deviation. It is crucial to remember that consulting with the local electrical inspector is paramount to confirm the applicability of Section 110.26(E's exception in a specific scenario. The inspector can provide invaluable guidance on any additional requirements or interpretations that may pertain to the project's location. To elaborate further on feeder tap rules in the context of Section 240.21.B.1, it's important to understand the underlying principles. The National Electrical Code aims to protect electrical systems and personnel from hazards. The tap rules are designed to minimize the risk of overcurrent situations leading to fires or equipment damage. The 10-foot tap rule, in particular, is intended to limit the length of unprotected conductors, reducing the potential for faults to escalate into serious problems. When tapping a large busbar, the available fault current can be very high. If a fault occurs on the tapped conductor before it reaches an overcurrent protection device, the entire busbar could feed the fault, potentially causing significant damage. While limiting the length of the tap conductor, the risk of such an event is reduced. Section 240.21 outlines various scenarios for feeder taps, each with specific requirements. These scenarios are based on factors such as the size of the tap conductor relative to the feeder, the length of the tap, and the type of occupancy. Each section provides rules designed to ensure adequate protection against overcurrent. Understanding these different scenarios is crucial for electrical designers and installers to ensure code compliance and safety. Now, focusing on the exception provided by Section 110.26(E), it's important to recognize that this exception is not a blanket waiver of workspace clearance requirement. It's intended to provide flexibility in situations where strict adherence to the rules is impractical or impossible, but only when safety is not compromised. When invoking this exception, the electrical designer must demonstrate that the proposed deviation does not create an increased risk of electrical shock or arc flash. This may involve providing additional protective measures, such as insulated barriers, remote racking systems, or enhanced personal protective equipment requirements. The decision to allow a deviation from workspace clearance requirements ultimately rests with the local electrical inspector. The inspector will consider the specific circumstances of the installation, the potential hazards, and the proposed mitigating measures. It's essential to provide the inspector with all the necessary information to make an informed decision, including detailed drawings, calculations, and a clear explanation of why the deviation is necessary. Furthermore, consider additional safety measures. Even when an exception is granted, Implementing extra safety precautions is always a good practice. This could include using arc-resistant switchgear, installing ground fault protection, or providing additional training to personnel who will be working on the equipment. Regular inspections and maintenance are also crucial to ensure the continued safe operation of the electrical system. Another important aspect to consider is the coordination of overcurrent protection devices. When tapping a feeder, it's essential to ensure that the overcurrent protection devices on the tap and the main feeder are properly coordinated. This means that the tap overcurrent device should trip before the main feeder overcurrent device in the event of a fault on the tap. Proper coordination helps to minimize the extent of the outage and prevent damage to the electrical system. Coordination studies should be performed by a qualified electrical engineer to ensure that the overcurrent protection devices are properly sized and set. The study should consider the available fault current, the characteristics of the loads, and the interrupting ratings of the overcurrent protection devices. The results of the coordination study should be documented and kept on file for future reference. When documenting the deviation from the standard conductor length requirement, it's important to be thorough and clear. The documentation should include a detailed explanation of why the deviation is necessary, a description of the proposed installation, and a list of any additional safety measures that will be implemented. The documentation should also include calculations to demonstrate that the proposed installation is safe and code compliant. The documentation should be reviewed and approved by a qualified electrical engineer. It should also be submitted to the local electrical inspector for approval. The electrical inspector may require additional information or modifications to the design before granting approval. Once the deviation has been approved, the documentation should be kept on file for future reference. It's also important to update the electrical drawings to reflect the actual installation. In addition to the technical aspects of the installation, it's also important to consider the human factors. Electrical workers should be properly trained on the hazards of working on or near energized equipment. They should also be provided with the appropriate personal protective equipment, such as arc flash suits, gloves, and face shields. Regular safety meetings should be held to reinforce safety procedures and address any concerns that workers may have. It's also important to establish a culture of safety within the organization. This means that everyone, from management to field workers, should be committed to safety. Safety should be a top priority in all aspects of the electrical installation and maintenance process. By following these recommendations, it's possible to address the challenges of workspace clearance while maintaining a safe and code-compliant electrical system. It's important to remember that electrical safety is a shared responsibility, and everyone involved in the project should be committed to ensuring a safe working environment. Let's delve deeper into the specifics of applying Section 110.26(e), the workspace exception, in this context. The exception hinges on the idea that deviations from standard workspace are permissible if necessary for maintenance and repairs. This necessity must be carefully evaluated and justified. Firstly, consider the frequency and nature of maintenance required for the fuse switch. Is it a type of switch that typically requires frequent inspections, lubrication, or component replacements? Or is it a relatively low-maintenance device? The less frequent the anticipated maintenance, the stronger the argument for invoking the exception. Secondly, assess the complexity of the maintenance tasks. Can most maintenance be performed with the switch de-energized? Or are there situations where live work might be necessary? If live work is anticipated, the workspace becomes even more critical, and justifying a deviation becomes more challenging. Thirdly, explore alternative switch designs or technologies that might reduce the need for maintenance or allow for remote operation. For example, a remotely operated switch could eliminate the need for personnel to enter the workspace during switching operations. Now, regarding the documentation required for the deviation, it should include a detailed risk assessment. This assessment should identify the potential hazards associated with the reduced workspace, such as arc flash, electrical shock, and physical injury. It should also outline the mitigating measures that will be implemented to minimize these risks. These measures could include enhanced personal protective equipment, insulated tools, barriers, and warning signs. The documentation should also include calculations demonstrating that the reduced workspace does not compromise the safety of personnel. These calculations should consider factors such as the available fault current, the arc flash boundary, and the approach distances for qualified electrical workers. The calculation should be performed by a qualified electrical engineer and should be reviewed by the local electrical inspector. Moreover, the documentation should clearly state the specific sections of the National Electrical Code that are being deviated from and the reasons for the deviation. It should also include a statement from a qualified electrical engineer certifying that the proposed installation is safe and code compliant despite the deviation. Furthermore, the documentation should include a detailed maintenance plan for the fuse switch. This plan should outline the frequency and type of maintenance that will be performed, as well as the procedures for safely performing the maintenance. The plan should also address the specific hazards associated with the reduced workspace and the mitigating measures that will be implemented. The maintenance plan should be reviewed and approved by the local electrical inspector. When presenting the documentation to the local electrical inspector, it's important to be prepared to answer questions and address any concerns they may have. The inspector is responsible for ensuring the safety of the electrical installation, and they will want to be satisfied that the proposed deviation does not create an unacceptable risk. Be prepared to provide additional information or make modifications to the design if necessary. It's also important to remember that the local electrical inspector has the final say on whether or not to approve the deviation. If the inspector denies the request, it's important to respect their decision and explore alternative solutions. There may be other ways to achieve the desired outcome while still complying with the National Electrical Code. For instance, consider rerouting the conductors, relocating the switchboard, or using a different type of overcurrent protection device. Remember, the primary goal is to ensure the safety of the electrical system and the personnel who will be working on it. Code compliance is essential, but safety should always be the top priority. In situations where code compliance and safety seem to be in conflict, it's important to consult with qualified electrical professionals and seek guidance from the local electrical inspector. Together, you can find solutions that meet the requirements of the National Electrical Code and ensure a safe working environment. To further elaborate on the considerations for maintenance and repair, it's helpful to categorize the types of maintenance that might be required. Firstly, there's preventative maintenance, which involves routine inspections, cleaning, and lubrication to prevent failures. Secondly, there's corrective maintenance, which involves repairing or replacing components that have failed. Thirdly, there's predictive maintenance, which involves using advanced techniques such as infrared thermography and vibration analysis to detect potential problems before they lead to failures. The frequency and type of maintenance required will depend on the specific type of fuse switch being used, its operating environment, and the criticality of the load it serves. For example, a fuse switch that is installed in a harsh environment and serves a critical load will likely require more frequent and thorough maintenance than a fuse switch that is installed in a clean environment and serves a non-critical load. When evaluating the need for live work, it's important to consider the potential hazards involved. Live work exposes personnel to the risk of electrical shock and arc flash, which can cause serious injuries or even death. Therefore, live work should only be performed when it is absolutely necessary and when all other options have been exhausted. If live work is unavoidable, it's essential to follow strict safety procedures and use appropriate personal protective equipment. This includes wearing arc flash suits, gloves, and face shields, as well as using insulated tools and equipment. It's also important to have a qualified observer present to monitor the work and provide assistance if needed. In addition to the technical considerations, it's also important to consider the economic factors. Deviating from the standard conductor length requirement may involve additional costs, such as the cost of rerouting the conductors or relocating the switchboard. These costs should be weighed against the benefits of maintaining proper workspace clearances and reducing the risk of electrical accidents. It's also important to consider the potential cost of downtime. If the fuse switch fails and requires repair, the downtime can be costly, especially if the load it serves is critical. By implementing a comprehensive maintenance plan and addressing potential problems before they lead to failures, it's possible to minimize the risk of downtime and save money in the long run. Finally, it's important to remember that the National Electrical Code is not a substitute for sound engineering judgment. The code provides minimum requirements for electrical safety, but it's up to qualified electrical professionals to design and install electrical systems that are safe and reliable. By carefully considering all of the factors involved and seeking guidance from the local electrical inspector, it's possible to achieve code compliance and ensure a safe working environment.